Suppose F is a partition of A, G is a partition of B, and the sets A and B are disjoint. Prove that the union of the two partitions is a partition of the union of the sets. Okay. So what does this look like? Well, we've got A over here somewhere. Call that the set A. And you've got another set B. And we're assuming they're disjoint, so they don't overlap at all. And then we have a partition F of A, which basically is, you know, a way of breaking A up into some pieces, such that their union is A, they're non-empty, and they don't overlap at all. Right? So F has, in this case, these 4 elements. And then we also have a partition G of B. Okay, so maybe I'll just split it up into 3 pieces. So that's my partition G. It's the family containing these 3 subsets of B. And now what I'm doing is considering the union of my sets, A union B. So that's just the 2 rectangles together. And then I'm also looking at the union of the partition, which means I'm taking these 4 subsets of A together with these 3 subsets of B. Right, so F union G is going to have 7 elements in this case. And the claim is that these 7 elements give 7 subsets of A union B, give us a partition of A union B. Right? And I mean, they certainly do. Their union of all 7 things is A union B. They don't overlap at all. Right? The things over here don't overlap with each other, but they also don't overlap with anything over here. That's because of this assumption that A and B are disjoint. And none of the 7 are non-empty because they weren't non-empty to begin with. Okay, so this is a very believable statement. And in fact, it's one that I think for me is easier to understand if I just go ahead and write out the proof. But I did go ahead and do the scratch work over on the left here for those of you for whom that might be helpful. So let's try and work that out first, and then we can talk through the proof. All right, so what I've put there so far is what it means for F to be a partition of A. Right? So union is A, it's a pairwise disjoint, and every element of F is non-empty subset. Same thing for G being a partition of B. And then we're assuming A and B are disjoint, and our goal is to prove that F union G is a partition of A union B. So we have a lot of things to work with. We have 3 separate goals. Let's take them one at a time. First, we'll show that the union of F union G is equal to A union B. And we'll do that by proving that for all Z, if Z is on the left side, Z is on the left side if and only if it's on the right side. Okay. And so let's actually go over to the proof right away for that. We decided to do just a chain of if and only ifs there. Okay, so I've gone ahead and said what I'm going to do. We're going to prove that this equation is true, this equality of sets. And so, you know, let Z be arbitrary. We're going to show that Z is on the left side if and only if it's on the right side. And so we have Z on the left side if and only if. Well, for Z to be in the union of a family, it means there exists a Z such that a capital Z, right, some set such that Z is in that family, F union G, and the element Z is in the set Z. Okay. Now sometimes we write this as there exists Z in F union G, like a bounded quantifier. That's fine. You could write that for the first step and then go ahead and change it to this afterwards. Because now I want all this to be together. Okay. So first of all, Z in F union G means that either Z is in the family F or Z is in the family G. And now I have an OR and an AND, so I can distribute the AND over the OR to get Z and F and Z, or Z and G and Z and Z. That's a tongue twister. Okay, and then next I have an existential quantifier and an OR, and I know I can distribute such a thing over an OR. So I have 2 separate statements now. And this first half here is exactly the definition of little z being an element of union of F. Okay, it's basically it's contained in some element of the family F. Oh, and that should be a curly F. Let me fix that. There we go. Okay, good. And then what else? Same thing over here. This is what it means for little z to be in the union of G. And then here's where we use our assumption, right? We're assuming that the union of F is A, since F was a partition. And so we can just replace union of f by a here, and similarly we're assuming union of g is b, so replace that, and we get z is in a or z is in b, which of course is the definition of z in a union b, which was our goal. Okay, so there we go. The union of these, union of this new family f union g is a union b. All right. Next, we're going to. Oh, okay. Good enough. Next, we're going to prove that f union g is pairwise disjoint. So there's the definition of that. Remember, for all x in the family and y in the family, if they're different, then they're disjoint, right? All right, so we can also bring down the fact that f and g are pairwise disjoint. We're probably going to have to use those. And moreover, a and b are disjoint, so their intersection is empty, okay? And then to prove this, we can let x and y be arbitrary elements of f union g. And then I have to prove this conditional. And I don't really know what to do with x not equal to y as a given, so I'm going to try to prove the contrapositive instead. I will suppose that x intersect y is not the empty set, and I'll prove the negation of this, namely that x equals y. Okay. And all right, what do these mean? Well, okay. It means that x is in f or x is in g, and moreover y is in f or y is in g. And if you take all the possible combinations of those, you get 4 different cases. Either they're both in f, they're both in g, or x is in f, y is in g, or vice versa. All right. So let's think through those cases. In case 1, when x and y are both in f, we're going to use the fact that f is pairwise disjoint. Okay. And we're going to do universal instantiation in the case where x is x and y is y. Okay. And so we get that this conditional is true. And then we're going to combine that with the fact that we know x and y are not disjoint, right? And that's going to give us that x and y actually must have been equal. Okay. If they have any overlap at all, they must actually be the same set. So that gives us our goal x equals y in case 1. And then in case 2 is quite similar, right? We're going to use the fact that this is true for x and y both in g in exactly the same way to get that x has to equal y in that case as well. And then in case 3, x and y live in different families. And what does that tell us about x and y? If x is in the family f, we know the union of f is a subset of a, right? In fact, it equals a. And so we, right, if it's, okay, so if x is in f, then, and the union of f is in a, that tells me that x has to be a subset of a. All right. And similarly, y has to be a subset of b. I'll let you think that one out a little bit more. So, okay, now we're also using that x and y are non-empty, so we have an element that's in both, right? We have some z that's in x intersect y, and we can do, okay, well, and we know that, I'm being a little bit sloppy here, but that's okay. We know that we have z in x, which together with this subset statement would tell us that z is in a, and similarly z in y would tell us that z is in b, and so we can basically replace x intersect y there by a intersect b. And we've found something in the intersection of a and b. That means that a intersect b is non-empty, and that contradicts what we had up here that they are empty. Right? That was an assumption of the problem. So we have a contradiction in that case. And in case 4, where x and y just kind of swap where they live, now x is in g and y is in f, we get a contradiction in exactly the same way. Okay. All right, goodness. So let's try and see how that would be written up. So next we prove that the union is pairwise disjoint. So what did we do? We let x and y be arbitrary elements of f union g. That was right there, right from up here. And we're going to show that if x, right, we're trying to prove this conditional, and we do that by bringing the negation of the consequent as our given and the negation of the antecedent as our new goal. Good. And then we had, okay, these two disjunctions here gave us our 4 cases. And so in case 1, we suppose they're both in F. And then because F is pairwise disjoint, which really what we're talking about is these statements here, where we could do universal instantiation to get this, and then okay, and these, okay, and then using modus tollens, then this statement together with that conditional gives us that this antecedent is false, so we get x equals y. Okay. Similarly, in case 2, we had a very similar type of argument. This statement up here again is going to combine with that conditional, which came from G being pairwise disjoint to give us x equals y again. And then in case 3, there's something to say. So suppose x is in F and y is in G, as we are, then, because F is a partition of A, that means that X is a subset of A, right? And because G is a partition of B, that means that Y is a subset of B. I mean, okay, you could prove that in another sentence or two, but we'll just take that as understood. And then because X intersect Y was non-empty, we had some element Z0 contained in both. Okay, but then combining that with what we have up here, the Z0 must also be in A and B, and that contradicts the assumption that A and B are disjoint. Okay. In case 4, we'll just say it's analogous to case 3. It's really nothing new there, just some letters swapping places. All right, and then finally we had our last goal that every element of this family is non-empty, and this is going to be pretty easy. So let Z be an arbitrary element of the union of the families, show it's non-empty. Well, okay, that means either Z is in F or it's in G. So we just have 2 cases, and remember, we know that from up here, every element of the family F is non-empty, and same thing for every element of the family G. And so bringing that down here, we can do a universal instantiation, replacing X by Z, and we get that Z is non-empty. And then another universal instantiation, replacing Y by Z, and we get that Z is non-empty again. So in either case, we have our goal. Okay, so this one's pretty easy to write up. Finally, we prove that every element Z in the new family is non-empty. So let Z be an arbitrary element. Suppose, okay, so 2 cases. If it's Z is in F, then because F's a partition of A, Z is non-empty. And if Z is in G, because G is a partition of B, Z is again non-empty. And that finishes the 3 parts of our proof that F union G, the union of 2 partitions, is a partition under the assumption that the 2 sets A and B are disjoint.